Okay. My name is Ola Mæhlen, and this is my trial lecture as part of my defense here at NTNU. The title of this lecture is Spectral and Pseudo-Spectral Methods in Numerical Analysis. Okay, the material from this talk will mostly be from the following book, more specifically Chapter 1, 2, 4, 5, and 7. Stephen Orsag, one of the authors of this book, is sort of the father figure of spectral methods. He was not the first to implement them, but he popularized the concept at the end of 1969, I think, according to Wikipedia. Okay, let's start with an example. Almost all explanations of spectral methods starts with the heat equation. So we have the following problem, and the first time you see the heat equation, it might not be so obvious how to solve it. It's a partial differential equation, which in itself is not easy, and then you have some boundary conditions that I've here set to 0, and you have initial conditions. But the idea of spectral methods is to break the solution up into natural components. And the natural components used here are sinus x, sinus 2x, sinus 3x, and etc. And the reasons that it is convenient to use sinus functions is because they are eigenvectors of the double derivative, and because they all satisfy the boundary conditions. They all vanish at x is equal to 0 and x is equal to pi. You can use sinus functions to approximate all square integrable functions from 0 to pi. So this last point might be a little bit surprising, because most people are used to the fact that cosines and sines can be used to approximate square integrable functions from minus pi to pi, so 2 pi periodic square integrable functions. But that actually implies that sines can be used to approximate square integrable functions on 0 to pi. And it's because sinus functions can approximate all 2 pi, odd 2 pi periodic functions. So the point is that you have a function from 0 to pi, and you can always think about it as sort of part of an odd function, odd 2 pi periodic function. Because if you try to, this one is 2 pi periodic, so this one can be approximated by cosines and sines. But because it's odd, the cosines will disappear, and you'll be left with a sine series. And since the sine series approximates f, in particular, it approximates f between 0 and pi. So that explains that. Okay. So far we've done nothing, but what we're gonna do is we're gonna try this ansatz. We're gonna try and see if we can find a solution of this form. We cannot find a solution of this form, but we will see it's a very good approximation. Let's start by sort of calculating the different parts of the equation of this ansatz. So the time derivative of this ansatz goes straight to the coefficients. Because we don't let the sinus functions depend on time, we let them be sort of only dependent on space variable, and we let the coefficients depend on time. So the time derivative goes directly to the coefficients. The double derivative goes directly to the sinus functions, and the double derivative of sine nx is minus n squared sine x. So this is precisely what has been written here. And then we're going to do one more thing. We're gonna replace G by sort of the best approximation we can have of G with the sinus functions that we have. This is because, well, it will be more clear later. Actually, I'll explain later. Let's just have the expression for G here for now, and I'll explain why we introduced Gn. Okay, but so back to the ansatz. We want the ansatz to satisfy the equation, and if we try to plug it into the equation and we set the derivative, the time derivative of the ansatz to be equal to the double derivative in space of the ansatz, we get this equation. Now, the only way this equation can hold is if the respective coefficients on each side in front of the same sign nx agree. So let me say that again. All the coefficients in front of sine 1x, the coefficient in front of sine 1x must be equal to the coefficient in front of sine 1x on the other. Okay, this is yeah. My point is that you have coefficients on the left-hand side and you have coefficients on the right-hand side, and the coefficients have to agree. I don't think I have to explain why that is true, but it's true because if you multiply with sine nx and integrate, this is precisely the type of equations you get. You get one for each n between 1 and capital N. And these equations, these ODEs, are easy to solve. You get an exponential. Oh, you get an sorry. You get. Oops, ska vi se. I just jumped a little bit. That was by accident. Boom, back. So yeah, so you get these solutions. We haven't used the initial condition, so we still have some parameters that we can tweak, and these parameters are the an of 0. Okay, so we've deduced if our ansatz is to solve the equation, then the coefficients must take the form written at the bottom of the page, and so you can plug that into the ansatz, and our ansatz now looks like this. Now we want our ansatz to solve not only solve the equation but to satisfy the boundary condition and the initial condition. The boundary condition is not a problem because all the sinus functions disappear at 0 and pi, but the initial condition must be satisfied. Now, that might be impossible. It might be impossible for UN to satisfy the boundary condition, but it will be possible to satisfy the boundary condition if we, instead of the actual initial condition, use the approximation. Because then we can argue again that now the coefficients have to agree, and now we get explicit expressions for an of 0. It is the Fourier coefficients of g of x, the initial condition. So boom, that's our ansatz. This we looked for a solution of this form, and this is sort of the best. This is the best approximation we can get, but yeah, we haven't compared it to the actual solution. So the actual solution is exactly the same type of series, except it's not finite; it goes on forever. And so the error is the following expression, and here the point is that. Yeah, so the equation at the very end only holds for times larger than 0. So for times, times equal to epsilon, all of a sudden you get exponential decay of the error. And yeah, so it's not just L2, it's L infinity as well. You really get something that sinks insanely fast. And so approaching this problem using sinus functions, it gives you a very, very, very fast conversion what do you say? Convergence rate? Convergence rate. A finite difference scheme will typically give what's called error of algebraic decay. But here we really got something that went much faster than algebraic. Here we got so it's faster than exponential as well. It's like it's like Gaussian decay of the error. Let's go see. I'm just gonna pause here. Okay, so let's take a look at another example. One of the problems about spectral methods is that it really it works extremely well when the solution is smooth, but it might not work so well when the solution is not smooth. So here is an example that is going to be less smooth. It might be surprising that this example is less smooth, because the only difference is that we introduced a 1 in the equation. Otherwise, it's exactly the same. And 1, the number 1, doesn't seem to be a very unsmooth term. But we'll see that this is actually a less smooth example. So we tried the same thing. We tried to find a solution to this equation. And as before, we have an ansatz, which is a finite sum of sines, and the time derivative and the space derivative is the same as before. Now we have one. Yeah, so this is the same. This is the same philosophy as before. We will not be able to solve the equation exactly, but we can solve the equation if we replace every object in the equation with sort of approximations. And by approximations, I mean the best approximation that our sines can give you. So we let this 1 be written as a sum of the sinus functions, where the coefficients are precisely the Fourier coefficients of 1. Now, it might not you might not see that it's the Fourier coefficients of 1, because the 1 is gone inside of the integral. I've not included it, but it's the same story as with g. It's the best in L2 sense, the best approximation you can have of the function 1 using these sinus functions. Now, because this integral is very explicit, you can actually calculate it, and it takes this value. So, as you see, the coefficients of 1, only the odd coefficients of 1 don't vanish. All the even ones vanish. Geometrically, this is not very hard to see, because geometrically, when n is even, there are equally many positive humps as there are negative humps of sinus nx, and so on the interval 0 pi, so it all cancels out. But that's not the case with when n is odd. Okay. I've written here 1 as slightly 1n as slightly more explicit sum. I've inserted the Fourier coefficients, and we do the same thing with g. With g, we cannot insert explicit expressions for g hat, but we can just add at the bottom what g hat is. We also added what on is. Okay, now, so now we have sort of calculated all the terms. We now want our ansatz to solve the equation in the best sense it can. So we insert the expression we have for 1n into the equation, and the expression we have for the time derivative of the ansatz and the double derivative of the ansatz, and then we get the equation that is written up. And as before, all the coefficients have to match, and so we get ODEs. Now, this ODE is a little bit more tricky to solve. Not very tricky, but a little bit more tricky. And the solution takes this form. Yeah. We'll get back to this to the terms here. Actually, I'll point it out right now. One important term is, as you see, when n becomes really large, both the exponentials are going to disappear. But what you will be left with, at least when n is odd, is 4 over pi n cubed. So already you can see that we don't expect to end up with a very, very fast convergence. Okay, and if you use the initial conditions, you again realize that the weights at 0 must be equal to the Fourier coefficients of g. So our ansatz this turnaround became the following expression, and again the full solution is just the same expression but summed to infinity. And now the error goes like 1 over capital M cubed, which is precisely due to the terms that was mentioned previously, 4 over pi n cubed. So this convergence rate is what you would expect from a finite difference scheme. So it's not good, not at all as fast as the previous example was, which was faster than any algebraic decay. So yeah, the reason that we get a slow convergence rate this time around is because of a hidden non-smooth part of the solution. So the source term and the boundary condition don't cooperate very well in this example. The source term wants to lift u up everywhere in space. It wants to it tries to make u grow at a rate 1 everywhere, but the boundary condition wants u to be equal to 0 at the boundary. So at the boundary, the source term is pushing upwards, and the boundary condition is forcing u to be 0. So there's a struggle going on there. To more clearly see what I'm talking about, we can calculate the terminal state. So we assume that the solution stops changing after a really long time, that it reaches a terminal state. So it stops changing with time, and we can set ut to be equal to 0, and we get this equation. This equation reads that the double derivative of u in space must be -1, and so it's a polynomial. In fact, it must be this polynomial because it has to satisfy the boundary conditions. Now, this polynomial is smooth on 0 and pi, and so far it doesn't seem like there's a non-smooth part in the problem, but we are approximating this function using sinus functions. And as before, sinus functions treat functions on 0 to pi as really odd functions from -pi to pi. So from the perspective of a sinus function, the way u really looks like is as a parabola that has been glued to itself, to the flipped version of itself, and this function, which is a parabola from 0 to pi and a parabola from -pi to pi, is discontinuous at x is equal to 0, because on the left-hand side, the double derivative is discontinuous, because on the left-hand side the double derivative will be 1, while on the right-hand side the double derivative will be -1. Now, this in fact means that the Fourier coefficients of u cannot vanish very quickly. For the rectangular function, you have a decay like 1 over n, and since this is not the rectangular function, it's something that is 2 orders more smooth in a sense. It goes like 1 over n cubed, the decay of the Fourier coefficients. But of course, what you always can is you can calculate the terminal state a priori, and you can subtract it from the function. So it might, although, so the original problem we want to solve is a partial differential equation, and it's not easy to solve a partial differential equation, but it might be easier to calculate the terminal state. And after doing that, we can introduce a new function vtx, which is u, but with the terminal state subtracted. Now, if we take the t derivative of v, it is exactly the same as the t derivative of u, but the space derivative is now shifted. It's shifted. It's the same as u, but with a +1, which is precisely because we've subtracted the terminal state. So now we actually, the equation we get for v is the heat equation with initial data. So we subtract this this terminal state, and we subtract it from everything. We subtract it from u, we subtract it from g. But the point is that if we now if we now apply the spectral methods that we did in the first example, but to v, we again get very, very rapid convergence. What slowed the convergence rate down was that there was this non-smooth piecewise polynomial that was thrown in. But yeah, as one can see here, it's possible to split it out. So this is also a part of spectral methods that one has to implement them right. One has to get rid of the rough terms if they can be gotten rid of, and the spectral methods will be very good at approximating what's left, if it's smooth, that is. So I should have added that a long time ago. The convergence rate of this V is very rapid. Okay, so the general idea of spectral methods is to solve partial differential equations by breaking the solution up into natural components. So it depends on the problem what a natural what components are natural to use. It should be easy to decompose the parts of the problem into the components. The equation should be simplified by this process, and if possible, one also hope for rapid convergence using these components. So it's a mix of efficiency and accuracy that one seek when using spectral methods. Now, the first example was a very successful application of spectral methods because here all these three parts were satisfied. Spectral methods and finite element methods are similar. It's this same idea of breaking a solution up into parts, but one difference is that the components or the basis functions you use for spectral methods are typically global in space, whereas the finite element method basis or components, they're usually local. Another difference is that for spectral methods, you really look for convenient properties to exploit in the equation, whereas finite element methods is often focused on the geometry of the space. Okay, some popular families of components or basis functions to use is sinusoids, which is what we've used in the first and second example. You can also use Legendre polynomials and Chebyshev polynomials. I'll talk quickly about what these polynomials are. So Legendre polynomials is a long family of polynomials. It is, I think, one that most graduate students have met because they form an orthogonal basis in the square integrable functions defined on the interval -1 to 1. So there you already have sort of a natural way to break any solution up into Legendre polynomials. Legendre polynomials also satisfy some algebraic properties and differential properties that can be used in a spectral method scheme. Similarly, the Chebyshev polynomials are also an infinite family of polynomials. They can be characterized with this formula, and by that I mean you can plug in cosine of theta instead of x, and you get this equality. So it only defines the polynomials on -1 to 1, but that's enough. Polynomials are characterized by their derivatives at any particular point. Okay. As was the case with the Legendre polynomials, the Chebyshev polynomials they also form an orthogonal basis, but in the weighted L2 room, where the weight is 1 minus x squared, 1 divided by the square root of 1 minus x squared is what I mean. And the Chebyshev polynomials also satisfy some algebraic properties and some differential properties. Yeah, so the second one is actually an integral formula. Yeah, so that's enough about the Chebyshev polynomials. So these are not the only families that are used in spectral methods, but it's sort of top 3 most popular. Okay, so in this talk we'll be focused on problems of this form. Okay, so the operator is in space, it's independent of time, does not change with time. The space is an open set in RD, and we will only be looking at homogeneous boundary conditions. This is because if we had a problem that was with not homogeneous boundary conditions, then we could introduce a function. So if we assume that the boundary conditions are a little bit smooth, we can introduce a smooth function b bar, which lives in our whole domain, but which agrees with the boundary condition b. And now if you subtract this b bar from the solution u, much like we did previously, you introduce a v, which is the solution, but slightly shifted. You've subtracted a function. Then what you get is something which satisfies the following equation. You take the t derivative, and is ut minus b bar t. Ut, you can replace ut by lu plus f. And if you also subtract and add L of... Okay, so there's a mistake in the... Okay. So it's supposed to be LB bar, not LB. Because what we've done here is we've added and subtracted LB bar. That's how you get LV. And this right-hand side is then LV plus F tilde. F tilde is defined as the whole expression. And not only does V satisfy this equation, but V has no boundary conditions. It vanishes at the boundary. Because at the boundary, U is equal to B and B bar agree on the boundary. So V vanish on the boundary, and its initial condition is a new initial condition where B bar has been subtracted from the original initial condition. So the point is that V solves a problem like the one below. So we're not going to be interested in non-homogeneous boundary conditions because they can be transformed into problems like the one below. Okay, so it's also possible, though I'm not going to spend much time on it because we'll see it later, It's also possible to sort of get rid of the source term in the sense that if we can, well, if the problem is well posed and there is a solution for all initial conditions in the homogeneous case, then Duhamel's principle tells you that there will be, at least for if f is a little bit smooth in time, that there will always be a solution with a source term as well. But we're not going to drop the source term. We're going to include the source term, although one could, so Duhamel's principle says that you can drop the source term and only focus on homogeneous problems, but we will not do that, because we will aim at sort of find a nice numerical method of explicitly calculating u, and Duhamel's principle doesn't necessarily simplify the goal. Okay, so we have a problem of this form with homogeneous boundary conditions and an initial condition. We're going to be working in a Hilbert space. That is, we assume that our solution takes values in a Hilbert space, which consists of functions on omega. It can be maybe square integrable or maybe a Sobolev space, but we assume it's a Hilbert space. B is going to be the subspace of H of functions that vanish on the boundary. We assume that G is an element of the Hilbert space and that F maps time into the Hilbert space in a continuous way. We also assume that L is well defined on a dense subset of the Hilbert space. And we assume that the problem is well posed, so that there's a unique solution for each initial condition. Okay, so we're going to attack this problem using spectral methods, and we do it by approximating the space B with an n-dimensional one, and we assume that B of n, that Bn also lies in the domain of the operator L, and we're going to let Pn be the orthogonal projection onto Bn. Now, we approximate the problem like this, so it's the exact same problem, except now we want to find a function un, which maps into Bn, into the finite dimensional space, and we replaced f and g by their projections down onto the space Bn. And the same goes for the operator L. The operator L has been composed with the projection operator. Now, we've dropped the boundary conditions, and that's because since working in B, everything satisfies, all the objects satisfy the boundary conditions. Okay, this particular approach, where every single part, when you use components that satisfies the boundary conditions, is really called the Galerkin spectral approach. There's another one called the tau approach, where you decompose U up into basis functions or components that don't need to satisfy the boundary conditions, but then you add some extra components to satisfy them. But we're not going to focus on the tau approach here. We're just going to use the Galerkin approach. Okay. We don't assume that f and g originally is in B, but it still might be that as n gets really large, we get good approximations. In the first example, we saw that any square integrable function could be approximated by sines on the interval 0 to pi, but that doesn't mean that every square integrable function must vanish at 0 and pi. Okay. So the idea is that we can break an ansatz, which is a solution to this approximated problem, up into a weighted sum of an orthonormal basis functions from an orthonormal basis of Bn. And exactly as we did previously, we can calculate the t-derivative, which goes straight on the coefficients of A, and then the operator ln is maybe a little bit more tricky here, but ln was just the original L, but then projected down onto the space again. So that's why it is a double sum, because the L lands on every single phi, but then when you project down again, you have to take the inner product with every single. So this is the inner product with respect to, this is the inner product from age that you see in this weighted sum. I'm not going to use a lot of time to explain this because I see that I'm running out of time already. Yeah, and you also get similar looking expressions for Fn and Gn. Now, because you want this equation to be satisfied, that the t-derivative is going to be Lu plus f, you can set everything equal to one another. So you get a bunch of ODEs for these coefficients. This is exactly as we saw in the examples, but there it was slightly more clear expressions, but it's the exact same approach. In matrix notation, which we're going to use here, any the solution of this approximated problem can be written precisely as a weighted sum using this orthonormal basis. And if we make a vector out of these weights that really are the unknowns that needs to be calculated, the vector satisfies the following ODE system of ODEs, where the matrix is the matrix of all the inner products between L of phi and other phi's, and the F's and the G's are precisely the inner products of F and inner products of G. Yeah, so this is sort of the raw procedure of how it's exactly the same as we saw in the examples, but this is how it's sort of done generally. The challenge is to pick sort of a good basis, good components. Yeah, it should be pointed out here that you actually can solve this equation typically using Duhamel's principle again, but I'm not going to focus too much on that. We are not going to use it right now. We're going to use a forward Euler scheme, which typically is just as well as Duhamel's principle is expensive. So to solve this equation, we use a forward Euler scheme, and a forward Euler scheme would be something like this, that small step forward is roughly just the derivative multiplied by that small step forward. Now, the expensive part in this forward Euler scheme is this matrix here, both because the matrix is heavy to calculate, it has a lot of inner products that needs to be computed, and it might not be so easy to compute these inner products. It might be it might not be computationally straightforward, and you have a matrix multiplication. So in order to reduce the cost computationally, this is where you can really simplify the problem. If, for example, your orthonormal bases are eigenvectors of the operator L, then B is a diagonal matrix. But of course, this is sort of a dream scenario, but it's not always possible to get a full family of eigenvectors of L. If L was just multiplication with X, for example, you would not get a full family of eigenvectors. You can also use what's called pseudo-spectral methods to dampen the cost of this B term. So pseudo-spectral methods are a way to reduce the cost of the orthogonal mapping Pn. And here's a quick explanation for how they are deployed. So pseudo-spectral methods, it's not that you don't use a set of basis functions. You still use a set of basis functions, but you only use the basis functions evaluated at endpoints in your domain. It's important that the basis functions don't look too much the same on these endpoints. More precisely, the basis functions, when evaluated at these endpoints, must create vectors, n vectors, capital N vectors, that are linearly independent. Another way to phrase this is to say that the matrix whose ij entry is phi I xj, this matrix must be invertible, okay? So it is sort of a way to it's a way to map the space Bn, which is spanned by your n basis functions, into Rn. Now, for any v living in Bn, you can calculate its coefficients by knowing what value v takes at these collocation points x1 up to xn. And if you make a vector of these values, the vector which is denoted boldface v, then that vector satisfies the equation which is written out, which is the matrix phi multiplied with the v bar. So the point is that for elements in Bn, one may now calculate its coefficients just by knowing its values at n points. So you don't need to do, for example, full integration. You don't need to do inner products. Of course, you still need to solve this matrix equation, but for sort of well-chosen collocation points, that might not be such a hard problem. For example, well, that is probably unlikely, but for example, if these collocation points are chosen such that at point xn, only phi n is non-zero, then it would be then phi would be a diagonal matrix. So that's probably not possible, but maybe you can get something which is not far away from being a diagonal matrix. Maybe only 2 or 3 diagonals, or a slightly thick diagonal. So this is the point, that calculating the projection might now reduce to a much more cheap problem, and this generalizes to general elements in your Hilbert space. You may assume that, or you can think that, okay, any element in your Hilbert space has a projection down to Bn, and in Bn we can calculate the coefficients of this projection by this matrix equality. So you use the same matrix equality, but you plug in the values of W at the collocation points, not the values of its projection. So typically you might not actually get the exact projection, but you might not be very far off. If I remember correctly, this type of approach, as capital N, so the dimension of the problem, gets very large, it has the same convergence rate typically. So it is just as asymptotically precise, but it's cheaper. It's a more efficient way to calculate these projections down. So this sort of explains the name pseudo-spectral methods. It's not that you don't break things up into components. It's more that you don't calculate the coefficients in front of the components precisely. You do sort of a quick, a cheaper and quicker, rougher estimate, but which is computationally much more cheap. Okay, so I think I overestimated how fast I would talk. Things took took a much longer time than I had anticipated. I still have a bunch of slides on stability, but I'm going to just mention a quick thing here. Yeah, so the stability analysis. I'm going to jump to slide 33, if that's possible. Let me see. I think so. Okay. So yeah, I'm going to end the talk now, but I'm just okay. So I'm not going to prove this Lux equivalence theorem, but so typically, if you want to study the convergence of your spectral method scheme, you can apply this very general theorem in numerical analysis called the Lux equivalence theorem, which says that if a scheme is consistent, and consistent in our setting, so in our set, it's not, yeah, a consistent scheme, it will vary on the particular type of approach you do. If you do finite difference methods, or if you do spectral methods. But in our scenario, the consistency is that the projections or the Bn space actually approximates also all of H. So consistency is up in the right corner, that the difference between the projection of an arbitrary element u in H and u itself, that difference goes to 0 as n goes to infinity. Lux equivalence theorem is that a consistent scheme is convergent if and only if it is stable. So convergent means precisely what we want it to mean. It means that our approximations converge. In fact, it's a slightly stronger statement here, because it's convergence even if you don't have the correct time plugged in, but you have some Tn that converges to T. And while stability means that the different schemes that you construct are well posed, and they have solution operators, and that these solution operators are uniformly bounded in N. So I have some slides that proves Lux equivalence theorem, but I don't have time to go through them. But sort of the conclusion of Lux equivalence theorem is, if you're worried about convergence, what you should focus on is stability. And typically that is how convergence is proved for a lot of numerical analysis. You use Lux equivalence theorem to say that okay, we prove stability. So in short, if you want to prove that your spectral method scheme converges, then you look at the problems, the approximated problems you get for each capital N, and the corresponding solution operators. And if the solution operators are uniformly bounded, uniform in capital N, then you will have convergence by Lux equivalence theorem. In the book I mentioned at the very start, they also study what's called algebraic stability, which is a weaker form of stability, but which is still interesting with regards to spectral methods, because you expect to get a very rapid convergence, typically better than any algebraic decay of error. And so you can allow for your scheme to not be perfectly stable. You can allow the solution operators to not be uniformly bounded in N, as long as the bound grows no faster than algebraic in N, capital N. But yeah, So the rest of the slides is really just a long argument of this Lux equivalence theorem, but it's not super related to spectral methods. It's more a general numerical analysis result. Okay, so I think I'll have to stop there. That was it.